Welcome to our deep dive into the world of superheavy elements.
Super heavy elements.
These aren't the elements you learned about in high school chemistry.
Oh.
We're talking about elements with atomic numbers greater than 103.
Right.
Elements that are so heavy they aren't found naturally.
Exactly.
We create them in laboratories.
Yeah, we smash liter atoms together at incredible speeds.
And as you might imagine, these superheavy elements are pretty unstable,
Unstable.
existing for mere fractions of a second in some cases.
Milliseconds.
So we're talking about elements like tennessine, livermorium, fluorovium, copernicium, the list goes on.
It does.
But what's the point of creating these elements if they disappear almost as quickly as they're formed?
Whoa.
What can we actually learn from something that exists for just milliseconds?
It might seem counterintuitive,
Yeah.
but these fleeting elements offer us a glimpse into the fundamental forces that govern the universe.
Okay.
Studying them helps us understand the limits of nuclear stability, how atoms are structured, and even gives us clues about the processes happening in extreme cosmic events like supernovae.
So by studying these elements, we're essentially recreating a tiny supernova in the lab.
In a way, yes.
That's pretty amazing.
It is.
Okay, let's start with tennessine, element 117.
Tennessine.
What can you tell me about this element? Where was it discovered?
Tennessine was discovered in 2010
Okay.
through a collaboration between scientists in Russia and the United States.
Wow.
It was created at the Joint Institute for Nuclear Research in Dubna, Russia.
Okay.
And you might be surprised to learn that some of the experiments were conducted at Oak Ridge National Laboratory, right here in Tennessee.
Wow, so close to home.
Yeah.
That's incredible. Now, I know these super heavy elements have incredibly short half-lives.
Yeah.
How long did tennessine stick around?
Well, its most stable isotope,
Okay.
Tennessine-294,
Tennessine 294.
has a half-life of a mere 51 milliseconds.
To put that into perspective, you
Yeah.
wouldn't even be able to blink before half of it had decayed into something else.
That's right.
51 milliseconds.
Yeah.
That seems almost impossible to study.
Yeah.
How do scientists even measure something that disappears that quickly?
It's a real testament to the ingenuity of these researchers.
Yeah.
They have developed incredibly sophisticated detection techniques
Okay.
to observe these elements in the brief moments they exist.
That's mind-blowing. It's like trying to study a lightning strike in the split second it flashes across the sky.
Exactly.
So we have tennessine, discovered through international collaboration,
Right.
existing for just a blink of an eye. What's next on our list?
Next up is livermorium,
Livermorium.
element 116.
Okay.
And it has a pretty interesting backstory.
Okay, livermorium. That name sounds familiar.
Yeah.
It has something to do with the liver.
Not quite.
Okay.
It's named after the Lawrence Berkeley National Laboratory in California.
Okay.
They played a key role in its discovery back in 2000,
Okay.
along with, you guessed it,
I'm going to guess Russia.
the Joint Institute for Nuclear Research in Russia.
So another international collaboration. These elements really are a global effort.
They are.
Now, what about livermorium's properties? Is it any more stable than tennessine?
Unfortunately not.
Okay.
Livermorium is also incredibly unstable.
Okay.
Its most stable isotope, livermorium-293, has a half-life of about 53 milliseconds.
Okay, so we're still in the milliseconds.
We are.
You see, with livermorium-293, the nucleus is so packed with protons that the strong nuclear force,
Yeah.
which normally holds the nucleus together,
Yes,
really struggles to keep it stable.
it does.
This leads to rapid alpha decay, where the nucleus ejects an alpha particle,
Right.
essentially transforming it into fluorovium in a fraction of a second.
Exactly.
Well, you mentioned isotopes and alpha decay.
Yeah,
Can you remind me what those are and why they're important in this context?
of course. You see, not all atoms of an element are exactly the same.
Okay.
They can have slightly different numbers of neutrons,
Okay.
and these variations are called isotopes.
Got it.
Some isotopes are more stable than others.
Right. And that's why we talk about the most stable isotope for each of these superheavy elements. Makes sense. Alpha decay is a type of radioactive decay where an unstable nucleus ejects an alpha particle, which is basically a helium nucleus, to become more stable.
So even though livermorium's most stable isotope only exists for a fraction of a second,
Right.
the fact that it decays in this specific way through alpha decay tells us something about its structure and the forces at play within the nucleus.
Exactly. It's like a tiny fingerprint that helps us understand the element's properties.
Fascinating. All right, what's the next super heavy element we're exploring?
Let's move on to fluorovium,
Fluorovium.
element 114.
114.
This one is named after a place
Oh.
very significant in the world of superheavy element research.
Oh, this is where it gets interesting. Tell me more.
Fluorovium was discovered in 1998
Okay.
at the Joint Institute for Nuclear Research in Dubna,
Dubna again?
but its name honors the Flerov Laboratory of Nuclear Reactions,
Okay.
the very place where it was born.
It's a scientific tribute to the birthplace of so many superheavy elements.
That's a great way to honor the legacy of this research.
It is.
So how does fluorovium stack up in terms of stability?
Okay.
Are we still in the realm of milliseconds?
So fluorovium is actually a bit more stable than the previous two.
Okay.
Its most stable isotope,
Uh-huh.
fluorovium-289, boasts a half-life of about 2.6 seconds.
2.6 seconds. That's practically an eternity compared to tennessine and livermorium.
It is.
Okay, I'm starting to see a pattern here.
Yeah.
It seems like as we go up in atomic number,
Okay.
these elements are sticking around a bit longer.
That's an interesting observation.
Yeah,
And it leads us to a fascinating concept called the island of stability.
the island of stability.
You see, some scientists theorize that there might be a region of the periodic table
Okay.
where super heavy elements with much longer half-lives exist.
Wait, so there could be super heavy elements out there
Potentially.
that are stable enough to be studied in more detail.
That's the idea.
That would be a game changer.
Absolutely. And that's what makes this research so exciting.
Yeah,
We're constantly pushing the boundaries of what we know.
right.
And who knows what we might discover next.
That's a perfect segue to our next element.
Okay.
What's next on our super heavy adventure?
Let's talk about copernicium.
For copernicium.
Element 112.
Copernicium. I feel like I've heard that name before.
Yeah,
Is it by any chance named after Copernicus,
you got it.
the astronomer?
Copernicium pays tribute to Nicholas Copernicus,
Wow.
the astronomer who revolutionized our understanding of the solar system with his heliocentric model.
Right.
The idea that the Earth and other planets revolve around the sun.
That's amazing. It's like connecting the vastness of space with these incredibly tiny, heavy elements.
Yeah.
So where was this cosmic element discovered?
Copernicium was discovered in 1996
Okay.
by a team at the GSI Helmholtz Center for Heavy Ion Research in Darmstadt, Germany.
Oh, yeah, so we're shifting gears from Russia to Germany. These discoveries truly are a global endeavor.
They are.
Now, what about copernicium's properties? How does it compare to the elements we've discussed so far?
Copernicium is actually one of the more stable super heavy elements we've encountered so far.
Oh.
Its most stable isotope, copernicium-285, has a half-life of about 29 seconds.
29 seconds. We're climbing the stability ladder.
Wow.
It's incredible to think that we've gone from milliseconds to almost half a minute.
I know.
This island of stability idea is starting to sound more and more plausible.
Is.
What's next on our list?
Next up is roentgenium,
Rowan ingenium.
element 111.
Rowan ingenium. Let me think. Wait a minute. Is it connected to X-rays?
You are absolutely right.
Oh, cool.
Roentgenium is named after Wilhelm Conrad Röntgen,
Okay.
the physicist who discovered X-rays in 1895.
Right.
A groundbreaking discovery that not only revolutionized medicine,
Yeah.
but also opened up a whole new way of seeing the world.
It's incredible how these super heavy elements not only push the boundaries of science, but also pay homage to the scientists who paved the way for these discoveries.
Right.
Where was roentgenium discovered? Was it another international collaboration?
Roentgenium was discovered in 1994
Okay.
at the GSI Helmholtz Center for Heavy Ion Research in Darmstadt, Germany,
Again.
the same place where copernicium was discovered.
Germany is becoming quite the hub for super heavy element research.
It seems so.
What about roentgenium's properties? Does it have a half-life similar to copernicium?
Roentgenium's most stable isotope,
Okay.
roentgenium-282, has a half-life of about 2.1 minutes.
2.1 minutes. That's a huge jump.
Mm-hmm.
It seems like the heavier we go, the longer these elements are sticking around.
Right.
Are we getting closer to that island of stability?
It's certainly a possibility.
Yeah.
Each new element we discover provides valuable data points that help us refine our models and theories about nuclear stability.
Uh-huh.
It's a constant process of discovery and refinement.
I love that. Okay, we're on a roll here.
Yeah.
What's the next super heavy element we'll be exploring?
Let's delve into Darmstadtium,
Darmstadtium.
element 110.
Okay.
This time, the naming convention takes a slightly different turn.
Darmstadtium. It definitely sounds German.
It is.
Is it named after the city of Darmstadt where it was discovered?
Precisely.
I knew it.
Darmstadtium was discovered in 1994
Okay.
at the GSI Helmholtz Center for Heavy Ion Research in Darmstadt,
Okay.
and they chose to honor the city itself.
I like that they named it after the city.
Yeah.
It's like Darmstadt has its own element on the periodic table now.
It does.
What about its properties?
Okay.
What can you tell me about Darmstadtium?
Darmstadtium's most stable isotope, Darmstadtium-281, has a half-life of about 10 seconds.
Okay, so back down to seconds. But we're still dealing with elements heavier than anything found in nature. Every second counts with these super heavy elements.
It does.
What's next on our journey?
Our next stop brings us to micnerium.
Micnerium.
Element 109.
Okay.
This element holds a special significance in the history of nuclear physics.
Micnerium. That one doesn't immediately ring a bell.
Oh.
What's the story behind this element's name?
Micnerium is named in honor of Lisa Meitner,
Lise Meitner.
an Austrian physicist who made groundbreaking contributions to the discovery of nuclear fission.
Wow.
She was a truly remarkable scientist who faced significant challenges in her career
Oh.
due to her gender and Jewish heritage.
Wow, her story is really inspiring.
It is.
It's a reminder that the pursuit of scientific knowledge is often driven by individuals who overcome tremendous obstacles, and their contributions should absolutely be celebrated.
They should.
So where was micnerium discovered?
It was discovered in 1982
Okay.
at, you guessed it,
Darmstadt.
the GSI Helmholtz Center for Heavy Ion Research in Darmstadt, Germany.
They really seem to have a knack for creating these super heavy elements.
We do.
It makes you wonder if there's something special about Darmstadt.
Right.
Maybe something in the water. Okay, enough with the jokes.
Haha.
Tell me, what about micnerium's properties? Does it have a relatively long half-life, like some of the other elements we've discussed?
Micnerium's most stable isotope, micnerium-278, has a half-life of about 7.6 seconds.
So back to the realm of fleeting existence, but as we've seen,
Yeah,
even these short lifetimes provide valuable insights to researchers.
they do.
All right, let's keep this super heavy element train rolling.
Okay.
What's next on our list?
Next up is hassium.
Hassium.
Element 108.
108.
Its name, like some of the others we've discussed, has a connection to its place of discovery.
Let me guess, is it named after Hesse?
You got it.
The German state where the GSI Helmholtz Center is located.
That's exactly right.
I was right.
Hassium's name comes from the Latin name for Hesse, Hassia. It's another example of these elements being named to honor the places and people involved in their discovery.
It's really cool how these names tie the elements back to their origins
Yeah,
and help us remember the incredible efforts that went into their creation.
I agree.
So tell me more about hassium. What about its properties? Is it relatively stable?
Hassium is actually one of the more stable, super heavy elements we've discussed today.
Okay.
Its most stable isotope,
Yeah.
Hassium-277, has a half-life of about 11 minutes.
Yeah, 11 minutes. That's amazing. We're really seeing how some of these super heavy elements are starting to stick around for a while.
We are.
This island of stability theory is looking more and more promising with every element we cover.
It is.
What's next on our super heavy element adventure?
Let's move on to bohrium,
Bohrium.
element 107.
Okay.
This time we have another element named after a scientific luminary.
Bohrium. Now that one definitely sparks a connection for me.
Okay.
Is it named after Niels Bohr,
It is.
the physicist who made those groundbreaking contributions to our understanding of atomic structure and quantum mechanics?
You are absolutely correct.
Awesome.
Bohrium is named in honor of Niels Bohr, a true giant in the world of physics.
Right.
It's a fitting tribute to his legacy, considering his work helped us understand the very building blocks of these super heavy elements.
That's amazing. It's like a full circle moment,
It is.
honoring the scientists who helped lay the foundation for these incredible discoveries.
I agree.
So where was bohrium discovered?
Bohrium was discovered in 1981
Okay.
at, you guessed it,
Darmstadt.
the GSI Helmholtz Center for Heavy Ion Research in Darmstadt, Germany.
They really are the super heavy element champions.
They are.
It's incredible how much they've contributed to this field.
It is.
Now, what about bohrium's properties? Does it have a long half-life like hassium?
While not quite as long-lived as hassium,
Okay.
bohrium's most stable isotope,
Okay.
bohrium-270, has a half-life of about 61 seconds.
Okay, so back down to the realm of seconds.
Yes,
But still very impressive considering how fleeting these super heavy elements are.
it is.
All right, we're getting close to the end of our list.
Okay.
What's the final super heavy element we'll be exploring today?
Our final stop on the super heavy element journey brings us to seaborgium,
Seaborgium.
element 106.
Seaborgium. That one doesn't immediately ring a bell. Who is this element named after?
Seaborgium is named after Glenn T. Seaborg,
Glenn T. Seaborg.
an American chemist who played a pivotal role in the discovery of many transuranium elements, including plutonium,
Wow.
He was a true pioneer in the field of nuclear chemistry, and his contributions earned him a Nobel Prize in Chemistry in 1951.
A Nobel Prize winner.
Oh.
It's incredible how many of these super heavy elements are connected to individuals who made such significant contributions to science.
It is.
Where was seaborgium discovered? Was it another discovery at the GSI in Darmstadt?
This time we're heading back to the United States.
Okay.
Seaborgium was discovered in 1974
Okay.
by a team of scientists at the Lawrence Berkeley National Laboratory in California.
Oh, that's right. We encountered this lab earlier when we discussed livermorium.
We did.
It's like we've come full circle on our super heavy element journey.
We have.
What about seaborgium's properties? How does it compare to the other elements we've discussed in terms of stability?
Seaborgium's most stable isotope,
Okay.
Seaborgium-271, has a half-life of about 1.9 minutes.
Not bad at all for a super heavy element. It's amazing to see how these elements, despite their fleeting existence, reveal so much about the nature of matter and expand our understanding of the universe.
That's exactly it. These elements challenge our understanding of the periodic table and raise interesting questions about the limits of nuclear stability. Who knows what other secrets they hold just waiting to be discovered?
It really does feel like we've just scratched the surface of this incredible world of super heavy elements.
It does.
Taking a step back to reflect on the bigger picture.
Yeah.
What does the study of super heavy elements teach us about the universe?
What's truly fascinating is that these super heavy elements don't exist naturally on Earth.
You're right. We've established that they're created in labs.
Yeah.
But why is that?
Well,
Are they just too heavy to form naturally?
it all comes down to stability.
Oh.
As you add more and more protons to an atom's nucleus, the forces that hold it together begin to weaken. The super heavy elements are so packed with protons that their nuclei are inherently unstable
Okay.
and decay very quickly.
So it's like trying to build a tower with blocks that just don't want to stick together.
Exactly.
Eventually, it all comes crashing down.
Exactly. And the heavier the element,
Yeah.
the faster that collapse happens.
Wow.
That's why we're talking about half-lives measured in milliseconds, seconds, or minutes,
Okay.
rather than the years, centuries, or even millennia we see with naturally occurring radioactive elements.
It's mind-boggling to think about elements existing for such brief periods,
Yeah.
yet still offering us so much information about the fundamental nature of matter.
They do.
It really is.
Yeah.
They give us a unique window into the extreme conditions that can exist in the universe.
Yeah.
Conditions we can't replicate on Earth,
Right.
except in these specialized labs.
Exactly.
So, if we connect this to the bigger picture,
Yeah.
what does the study of super heavy elements tell us about the universe?
Okay.
I mean, if they don't exist naturally here, where could they possibly be found?
That's one of the most exciting aspects of this research.
Okay.
Scientists believe that super heavy elements may be created in extremely energetic cosmic events,
Okay.
like supernova explosions or when neutron stars collide.
Wow. So by studying these elements created here on Earth,
Yes.
we're actually gaining insights into the most powerful events happening in the vastness of space.
Precisely. It's like having a tiny piece of a supernova right here in the lab.
Right.
By analyzing these elements' properties,
Yeah.
we can begin to understand what happens in these extreme environments.
Like cosmic forensics.
It is.
We're using these elements to unlock secrets about the universe's most dramatic events. It's incredible.
It really is. And remember, this research is still in its early stages.
Really?
These discoveries are relatively recent, and there's still so much more to learn.
Which leads to an important question. What could the future hold for this research? Could we discover even heavier elements? Will these elements ever have practical applications?
Those are the million-dollar questions.
They are.
Scientists are constantly pushing the boundaries,
Yeah.
trying to create elements with even higher atomic numbers.
So there might be a whole other row on the periodic table waiting to be filled. That's exciting.
Exactly. Who knows what properties those undiscovered elements might possess?
Right.
It's truly a frontier of science.
And what about practical applications?
Okay.
I know their instability makes it challenging to use them in everyday life.
Right.
But is there any hope for future applications?
That's where things get speculative.
Okay.
Some scientists believe that if we can create super heavy elements with longer half-lives,
Yeah.
they could potentially revolutionize various fields like medicine, energy production,
Really?
or even space travel.
Now we're talking science fiction.
Yeah.
But I have to ask how.
It all comes down to their unique nuclear properties.
Okay.
Imagine a super heavy element that decays in a very specific way,
Okay.
releasing a precise amount of energy. This could be harnessed for targeted cancer therapies or incredibly efficient energy sources.
So it's like finding a way to control those tiny nuclear explosions we talked about earlier.
Yeah.
And using them for good.
In a sense, yes. However, we're talking about a level of control and precision that is far beyond our current capabilities.
Not impossible.
Definitely not. As our understanding of superheavy elements expands
Yeah.
and our technology advances,
Mhm.
who knows what the future holds?
I love that sense of possibility. It's like we've opened a door to a whole new realm of scientific exploration.
And it's a door that will only open wider as we continue to delve deeper into the mysteries of these fascinating elements.
It seems like our journey into the world of superheavy elements has taken us from the smallest building blocks of matter to the most powerful events in the universe. We've even gotten a glimpse into a potential future where these elements could revolutionize our lives.
It's been a fascinating journey, and it truly speaks to the power of scientific curiosity and the relentless pursuit of knowledge.
Couldn't have said it better myself. Before we finish up,
Yeah.
I want to leave our listeners with something to ponder.
Okay.
We've discussed how these superheavy elements push the boundaries of the periodic table.
Right.
But is there an end in sight?
Hmm.
Is there a point where we can't create heavier elements?
Okay.
Or could we keep going,
Right.
discovering elements with even stranger properties and shorter lifespans?
That's an incredible question, and to be honest, we don't have a definite answer.
Oh, really?
Scientists are actively working on this question. It's a real challenge,
Yeah.
because as we try to create heavier and heavier elements,
Okay.
we need more powerful particle accelerators, more sensitive detectors.
Yeah.
And the experiments themselves become incredibly complex and expensive.
I can imagine. I mean, we're essentially trying to recreate conditions that only exist in the hearts of stars or during these cataclysmic events in space.
Right.
It's mind-blowing.
It is, and it really pushes the limits of our current technology and understanding.
So is there like a theoretical limit to how heavy an element can be?
That's a question that's still up for debate.
Okay.
You see, according to our current models of the atom, there may be a point
Okay.
where the nucleus simply cannot hold any more protons,
Right.
no matter how hard we try to force them in.
So it's like there's a maximum capacity for the nucleus.
In a way, yes. It's like trying to squeeze too many people into a tiny room. Eventually, there's just no more space.
Right.
And the same principle applies to the nucleus at a certain point.
Okay.
The repulsive forces between the protons become so strong that they overcome the strong nuclear force.
Yeah.
Which is what holds the nucleus together.
And the whole thing just falls apart.
Exactly. And that point of no return,
Okay.
that theoretical limit to how heavy an element can be,
Right.
that's what scientists are trying to figure out.
It's like a fundamental limit to the building blocks of the universe.
It is, and it really makes you wonder about the nature of reality and the forces that govern it.
It's incredible. Well, on that note, I think it's time to wrap up our deep dive into the world of superheavy elements.
I agree.
We've covered a lot of ground today.
We have.
From the discovery of these elusive elements
Yeah.
to their incredibly short lifespans,
Right.
to the mind-boggling theories about their potential applications.
And the possibility of an island of stability.
Oh, yeah. The island of stability. Don't forget that.
Right. A whole region of the periodic table
Yeah.
just waiting to be explored.
Waiting to be discovered.
It's truly a frontier of science.
It is. And who knows what incredible discoveries await us in the years to come.
Exactly. It's an exciting time to be following this field.
It really is.
Yeah.
So to our listeners,
Yes.
we hope this deep dive has sparked your curiosity
I hope so.
and inspired you to learn more about this fascinating and ever-evolving field of superheavy element research.
Absolutely.
And remember,
Yeah.
the journey of discovery never truly ends.
It doesn't.
There's always something new to learn,
Always.
something new to explore.
That's right.
So keep asking questions
Keep exploring.
and keep pushing the boundaries of what we know about the universe.
That's what it's all about.
Thanks for joining us on this incredible adventure.
It's been a pleasure. It really is a fascinating field.
It is. And you know, it's not just about the science.
Oh, no.
No, it's also about the human stories behind these discoveries.
Right, like Lise Meitner,
Exactly.
a woman who made incredible contributions,
Yeah.
but faced so many obstacles in her time.
It's really inspiring.
It is, and it's a reminder that science is a human endeavor,
Yeah.
driven by passion, curiosity, and perseverance.
And collaboration. I mean, we've seen how many of these discoveries involve teams of scientists from all over the world
Absolutely, it's a global effort.
working together to unlock the secrets of the universe.
It really is a beautiful thing.
It is. Well, I think we've covered just about everything there is to know about super heavy elements.
At least for now.
Right. Who knows what new discoveries await us in the future?
Exactly. That's the beauty of science.
It's always evolving, always pushing the boundaries of what we know.
And that's what makes it so exciting.
It really does. Well, on that note,
Yeah.
I'd like to thank you for joining us on this deep dive into the incredible world of super heavy elements.
It's been a pleasure.
And to our listeners, we hope you've enjoyed this journey as much as we have.
I hope so.
And remember, the universe is full of mysteries waiting to be unraveled. So never stop exploring, never stop asking questions, and never stop learning.
Well said.
Thanks for listening.